Okay, so let's talk about projectile motion. So say you have a ball and you shoot this ball or you kick this ball, whatever, with an angle. And this creates a velocity. So we call this V. And this velocity is angled. So let's say it causes an angle theta, right? So what happens here is that similar to forces in two dimensions, you can split this velocity into two components, and this works with any vector quantity, right? So we're going to split this velocity into two components. The first component, we're going to call it, which is this part right here, we're going to call it Vx, which is the x component of velocity. And then the second component, we're just going to call it Vy. And this is going to be the y component or the vertical component of velocity, where just to recap, Vx is equal to V cosine theta, Vx initial is equal to V cosine theta, and Vy initial is equal to V sine theta. Okay, well, let's discuss the path that an object like this takes. So the simplest path that a projectile like this can take is a parabolic path. So it'll look something like this. Right? If this was your object and you launched it, like say this velocity v. In this case, right, a few things that you have to know is that Vx, right, at any point of this path, so at this point at the peak, at this point at the end, at this point at the beginning, every point that you could possibly take at every stage of this motion, Vx, right, will always be equal to V cosine theta. It's constant because we're ignoring air resistance, so there is no force interacting to change it on the x-axis. So it's always V cosine theta. That's Vx. Vy, on the other hand, changes. It can change depending on where you take it. So at the beginning, Vy would just be as you see, we said Vy initial. It is just going to be V sine theta. But if we take it up here, right, at this point in the middle, at the peak, right, then at the peak we can say that V, similar to say a free fall, right, we can say Vy is equal to 0. But Vx is constant. Vx is still V cosine theta. So at this point, Vx is still V cosine theta. And another thing that you have to know is that if at the end I have Vy, if I wanted to find out the final speed of the object, right, or if this is like V initial, this is V initial, and I wanted to find the V here, which would look something like this. This is like V final, right? V final is just going to be V final is equal to radical, similar to any vector quantity, Vx squared, which is just V cosine theta, but we'll just write Vx squared, plus V Vy final squared. So you need the final y velocity here. And if you're wondering why we didn't write Vx final, it's because Vx final is the same as Vx initial. Vx is constant. It's always just V cosine theta. Now let's write some famous kinematic equations. So you've got some for the y-axis, for the y-axis, and you got some useful ones for the x-axis, and they work for both, but um, some are more useful when you use them on the y-axis versus the x-axis. So, for example, formula number one. Actually, let's make this a different color. Let's say y-axis. So you can say the change in velocity y is equal to the acceleration, which would just be gravity, so negative, or let's just keep it gt. Right? This comes from delta v equals at, where acceleration is just going to be gravity. The second equation is that delta h, or the displacement on the y-axis, we'll just call it delta y, is equal to half gt squared plus vyi, so the initial vertical velocity multiplied by the time. Now for the x-axis, some useful formulas there would be, so x-axis would be the change in x, or the range, right? Displacement is equivalent to Vx times t. This is a really important formula. People usually ask for the range, and if you rearrange this formula to be time independent, then you get delta x equals v squared 2v squared, or sorry, v squared sine 2 theta over g. Okay, so this is just the second version of this formula. Okay, and then another formula that can sometimes be useful for the y-axis would be delta y, or displacement of y, this time it's time independent, is equivalent to v final, vy final, let's call it vy final squared minus vy initial squared over 2g. These are the most important formulas that you need to know. Also, it is important to note that this formula right here, or this part of the formula with v squared sine of 2 theta over g, only works if your projectile was launched like this, so it lands in the same place that it was launched from. Right? If your projectile is launched from, say, a cliff or something, and looks something more like this, right? If that's your projectile right here, this is like the path it goes, then the second formula no longer works, but the first one works. So you're going to need to find total time, multiply it with Vx. Okay, so we have an exercise here which tells you that ball rolls horizontally with a certain speed, and it asks you for this specific scenario, what does that speed have to be for you to have for it to hit the target, right? So all you have to do here is, first of all, you have to break it into components. You have to see. So this is V. We want V. We don't know what that is, right? So if you look at V, you realize V does not have a Y. So Vy in this case is equal to 0. Vy initial, right? Just by looking at it, and if you can't tell just by looking at it, then you can say that the angle is 0, and then you can say Vy is equal to V sine of 0, and sine of 0 is 0, so Vy initial is 0, right? So now V of x is equal to V cosine 0, if you want to take it using the angle of 0, which is just V cosine 0. Cosine of 0 equates to 1, so you get Vx equal to V. Right, now we want to know what is the speed that will get me to hit that target. So that target has displacement of 3. So what do I have? I have delta x. Let me change colors. I have delta x equal to 3. And what I want is v of x, or v. In this case, it's the same thing. Right? So I want vx equal question mark. So what I have to do is I just have to use this formula. I have to use delta x is equivalent to v of x multiplied by time. So now I just need to find the total time, right? And the way you do that is you're gonna look here. I have the y displacement, so I have delta y equal negative 10. Why negative 10? It's because it goes 10 meters downwards, so we're just going to say negative 10. And I know that I have a formula that goes a little something like this. Delta y equals half gt squared plus viy t. So using this formula, I can find t, right? So this whole entire part here is 0 because vy is 0. And then we can plug in. We can say delta y is negative 10. So this is negative 10 is equal to half. G is negative, we're going to consider it negative 10. You can consider it negative 9.8 if you'd like. Multiplied with t squared. If you solve this equation either with shift solve or you just do the math, you'll get that t is equal radical 2. And now all you have to do is plug this in here, right? So you get delta x, which is 3, is equal to Vx equal to Vx multiplied with radical 2, divide by radical 2 on both sides, you get your answer, which is that Vx is equal to 3 over radical 2, and if you don't want a radical in the denominator, so that would just be 3 radical 2 over 2. And that's your final answer. Note that you cannot use the other formula that says that delta x You cannot use this formula in this case. Delta x equals 2v squared, or sorry, it's not 2v squared, v squared sine of 2 theta over g in this case, because the path that this projectile is going to take is not a perfect parabola. It doesn't look like this, it looks like this, as you can see. So again, this formula to the top left only works if your projectile is a perfect parabola that looks like this, i.e. it lands on the same height that it's launched from.
That'll be it for lesson 6.1, projectile motion. If you have any questions or want to ask anything at all, you can ask it down below in the comment section or in the server. And yeah, good luck.